So let's think for a minute about designing a buffer. Suppose you wanted to create a buffer at a particular pH. What do you need to think about? Well, you need to think about the ratio of your acid to the conjugate, and you need to think about the pKa of the acid and the pH that's desired. So here is a generic equation for an acid in water. So we have our acid HA in water forming hydronium ions and our conjugate base. And now we're going to do a little derivation to come up with an equation that will be useful to you in thinking about buffers and designing buffers. So we can write a generic term for Ka. Ka equals products over reactants. And so we have our hydronium ions, our conjugate base over our acid. And now we can take this term and rearrange it. So we can pull hydronium ion concentration over to one side. And now we're going to take the logs of both sides. So we get the log of hydronium ion concentration, the log of Ka, and the log of HA concentration over A minus concentration. And now we're going to multiply everything by a negative sign. So we have minus logs of things. And I'm just going to move this now up to the top of the screen. And we have this equation. So what is minus log of hydronium ion concentration? pH. What's minus log of Ka? pKa. So we have pH equals pKa minus the log of the concentration of your acid over the concentration of your conjugate base. And these are equilibrium concentrations for that, because remember, we derived it from our equilibrium expression for Ka. But a lot of times when you're working buffer problems, you know the concentrations that you added of these things, not necessarily the concentrations of equilibrium. And if we rewrite this expression in terms of the initial concentrations or original or O concentrations, then we have pH is approximately equal to pKa minus log of the initial concentrations of your acid over your conjugate base. And this is known as the Henderson-Hasselbalch equation. And people love the Henderson-Hasselbalch equation, and it can be incredibly useful to you in solving these problems. But I'm going to emphasize when it's okay to use it and when it's not okay to use it, because people try to apply it to everything. And it's for buffer problems, and people apply it to all sorts of things that are not buffer problems. So I want to make sure that it's clear when you can use it and when you can't use it. And it's fine to use it and you should use it when it's acceptable, but not at other times. It's one of the few equations in acid-base, so people get very excited by it. All right, so remember that it's really equal when they're at equilibrium concentrations, and this is just an approximation that we're saying that those are initial concentrations. So when is it okay to say, well, the equilibrium concentration is more or less the same as the initial concentration? And that's true when X, which is in this particular example, your hydronium ion concentration, is small compared to your initial concentration of the acid and the conjugate base that you added to the buffer. So, and when X is small, then pretty much the equilibrium concentration equals the initial concentration. So there's not really very much change if X is a really small number. So a lot of the time this is true. Remember, we're making buffers from weak acids and weak conjugate bases. And the definition of a weak acid is that it only loses a tiny fraction of its protons. It only ionizes slightly in water. And a weak base typically only accepts a fraction of the protons it can accept. It's a weak base, so it's not doing a whole lot of chemistry there. So this approximation is good a lot of the time. So just so you know when you can and cannot use it, we're going to give a rule and say it's the same rule as before. When we say when X is small or your hydronium ion concentration is small compared to the acid or the conjugate base, When it's less than 5%, that's what we're going to call small, less than 5%. So the same rule we've been using all along. When x is small, this approximation works pretty well, and you can plug in your concentrations right there. Your initial concentration is not your equilibrium concentration.